I should start by introducing myself. My name is Cynthia Henson. I work at Fraser University, Faculty of Science, and I do look after the outreach and engagement program of the faculty. I will be your host for this afternoon. And with me on this webinar are Dr. David Stenning, a faculty member of our Department of Statistics, and one of his master's students, Yue Yan. And this Meet an SFU Scientist session is all part of Science Rendezvous. Science Rendezvous is a science fair celebrated across Canada, and we do this every year, and we've been doing this for over a decade now. And this science fair brings together scientists from different host institutions celebrating science contributions and learning. And Fraser University is one of the major states in Colombia, and we always follow the astronomy theme, also because we like to celebrate International Astronomy Day around this time. So this session we're about to have for this afternoon is titled Meet an SFU Scientist. This session allows you to get to know some of our faculty, what their research interests are, and it engages the community, that's you, in discussions about this research work. Just a few house rules and reminders before I hand it over to our presenter. The live transcription has been enabled. Feel free to turn that on if you find that useful. This session is also being recorded, and the link will be shared on our website and YouTube channels, so stay tuned for that if you want to look back at the session. The chat page has been turned off, but there is a Q&A box that you should be seeing on your screen. We encourage you to use that box to type in any comments or questions you might have for our presenters today. Also, after today's session, we will be sending you by email a feedback web survey link. We'd love to hear from you. You might have some comments or suggestions about today's presentation and other future events of outreach and engagement by the Faculty of Science. All right, so today's description of our topic is actually all about astrostatistics. Modern astronomy contends with complex physics, complex instrumentation, and complex data. The result is an abundance of complex statistical challenges. This talk this afternoon will focus on how new research in the exciting interdisciplinary research field of astrostatistics is advancing both astronomy and statistics, with applications in such diverse areas as predicting solar activity and space weather, discovering Earth-like exoplanets, and even learning about cosmology and the fate of our years. Dr. David Stenning is an assistant professor at the Department of Statistics and Actuarial Science here at Fraser University Science. His research interest is on statistical methods for the physical sciences, specifically astronomy and astrophysics. On the statistics side, Dr. Stenning utilized complex computer simulations of astrophysical phenomena, along with modern machine learning and data science techniques to tackle challenging scientific problems. Presenting with David today is one of his master students, Yue Yan. Yue Yan is supervised by Dr. Stenning, and he's also working on a project that uses statistical approaches to improve solar cycle prediction. So I don't want to take too much time. I'd like to turn the floor over now to David and Yue. Over to you for your presentation today. Thank you so much.
Thank you, Cynthia, for that kind introduction. I'll go ahead now and just begin my presentation. So as you just heard, this talk is all about astrostatistics, which is a bit of a made-up word. It's a portmanteau of astronomy or astrophysics and statistics. And as its name implies, it's all about developing statistical methods that are motivated by solving problems coming from astronomy or astrophysics. And it's said that this is an emerging interdisciplinary area. And so why is this becoming a new field now? Like, astronomy has been around for centuries. Statistics has been around for not quite as long, perhaps, but still for a long time. So why is astrostatistics being a word that has only recently come into use? And the reason for this is that modern observatories, modern instruments, space-based telescopes, and ground-based instruments are generating just enormous and vast amounts of data. So currently we have instruments that are monitoring the night sky in pretty much the entire electromagnetic spectrum, from radio waves at one end through to visible light, the portion of the light that we can actually see with our own eyes, which is just a very narrow part of the spectrum, all the way through ultraviolet light, X-rays, and gamma rays. You might have also heard recently about the discovery of gravitational waves, which won a recent Nobel Prize in physics. And so this is giving us yet another way of observing the universe and trying to learn something about the universe in which we live. But along with these new observatories that are generating simply vast amounts of data come challenges. The techniques that historically have been used to process and analyze astrophysical data simply can't be done with the large amount of data that is currently being collected. And so this leads to both a challenge, but also an opportunity for astronomy. And this is an opportunity also to statisticians because it motivates us to create new statistical methodology that is geared towards solving some of the most complex and challenging, but also interesting scientific problems arising from astronomy today. And so for this talk in particular, I'm going to focus on a few different applications that I've worked on during my career as an astrostatistician. So the first of these is going to be in the area of stellar evolution, which is learning how stars form and evolve, which in turn informs astronomers about how our galaxy formed and evolved, and ultimately tells us some information about the formation history and evolution of our universe. And so this work was really motivated by a recently launched space telescope that is known as Gaia. So this was launched by the European Space Agency a few years ago. And the goal of Gaia is to construct the largest and most precise 3D catalog of our galaxy to date. And to do this, it's going to collect data on over 1 billion astronomical objects. So whereas in the past, scientists might have actually been looking at individual images or photographs and comparing them to see which objects are moving, how they're moving, and so on and so forth, that simply isn't practical when you have to do this for billions of objects and vast amounts of data. So that was motivating our approach, our desire to develop new statistical methods. And so this is one of the results that Gaia has put forth already, which is learning the proper motion of stars within our galaxy. So the proper motion is how stars appear to move to us as observers on Earth. And so this is useful information because if we know how stars are moving, we can understand certain properties of the galaxy, and we can also learn certain properties of the stars themselves. So in particular, we can learn which stars belong to star clusters, as we see here on the right. And these star clusters are going to be groups of stars that formed at roughly the same time from a common molecular cloud. And so they're going to share certain physical properties that we wish to infer. What I have here on the left is an example of what's known as a Hertzsprung-Russell diagram, or an HR diagram for short. And this is a diagram that's been used for a long time to study stellar evolution. So what it does is it plots a star's brightness on the vertical or y-axis against its temperature on the horizontal or x-axis. One thing you might notice is that maybe perhaps a bit unhelpfully, lower temperatures appear to the right on this axis, higher temperatures appear to the left. I'm not sure why Hertzsprung and Russell decided to make the diagram in this way, but they did, and it's been used this way ever since. So I should say that this diagram was independently discovered by Hertzsprung and Russell in 1911 and 1913, respectively. And it was I say discovered because they were trying to do kind of some simple exploratory statistics to learn whether there's something about stars, their properties that can be gleaned from just looking at simple plots of their data. So in some sense, Hertzsprung and Russell were acting like kind of proto-astrostatisticians more than 100 years ago. And the reason why this is such a useful diagram, and if you have taken any introductory astronomy courses, you've almost certainly encountered it previously. This is because it tells a story about the life cycle of a star, about stellar evolution. And so a star, and for now we can consider a star like our sun, forms when a dense region of a molecular cloud collapses under its own gravity. So out in space, there are these clouds of gases, and they're so vast that their own galaxy, their own gravity, can sometimes cause them to collapse in on themselves. And when this happens, assuming that there's sufficient mass, then because the gravity is so strong, it makes these collapsed regions so dense that nuclear fusion is ignited and the star is born. So during this phase of a star's life cycle, it's burning hydrogen into helium and releasing energy out into space. And when this is happening, the star lies somewhere along this portion of the HR diagram known as the main sequence. So stars that are more massive are going to lie to the top and to the left on the main sequence, and stars that are less massive lie lower and to the right. Our own star, the sun, is somewhere in between, so it lies kind of in the middle of this main sequence. And so this phase, when the star is burning hydrogen into helium, lasts for millions of years on the upper left portion of the diagram, to billions of years on the lower right portion, depending on that initial mass. And this is because stars that are more massive burn faster and die young. So if you're a little bit older, you might get that kind of a reference. But what happens once the star begins to run out of helium? Once the star runs out of hydrogen. So for a long time, the star is simply fusing hydrogen into helium, but eventually that fuel is going to run out. So when this happens, the core of the star collapses and its temperature increases. But at the same time, the star itself expands. So the surface, if you will, of the star expands, and that surface temperature is going to cool. So this results in a star that's brighter, but also cooler, at least on its surface. And when this happens, the star migrates to this giant branch of this HR diagram. So the star becomes a red giant. And so this is something that's going to happen to our own sun eventually, but not for billions of years. So it's not something that we personally have to worry about. So at this stage, when the star is a red giant, it's fusing helium into even heavier elements. And this phase lasts for a relatively short time in the life cycle of the star, only about 1/10 the time of the hydrogen burning phase. And eventually, the star is going to run out of helium and fuel for doing nuclear reactions altogether. And when this happens, there's no more energy kind of radiating outwards from the core. And so the core of the star is going to collapse in on itself, while at the same time, the outer layers of the star blow away. And so when this happens, the star migrates from this giant branch down to this region over here where we have white dwarfs. And so all that remains at this point is the small and dense core of the star, which is termed a white dwarf because they appear white to us. The light appears white when viewed through our telescopes, and dwarf star because they're very, very small relative to the size of other stars. And so they're no longer burning nuclear fuel. They're just this small ball of degenerate matter. And then this star will remain in this phase for a very long time. And so HR diagrams have historically been used to explain this life cycle of the star, of forming and lying somewhere along the main sequence, turning off the main sequence into the giant branch when it runs out of hydrogen, and then when it runs out of helium or heavier elements, migrating down to the white dwarf region where it remains for the rest of its life. So you might be asking, why am I talking about this? What does this have to do with statistics? And so the reason why I learned this and why I've used HR diagrams as a statistician primarily is that while these are useful for learning about stellar evolution, actually constructing these from observed data, such as a globular cluster that we observe here on the right, can be extremely challenging. So if we look at this figure, then the vertical axis plots the brightness of the star. And this is the absolute brightness. So this is how bright the star would be if it were at a fixed distance from Earth. So you might immediately notice a problem with that, which is that we can't set the distance from the star to the Earth. It's just out there somewhere in space. And that's a little bit of a problem because objects, stars that are farther away are going to naturally appear dimmer than if they were closer. So you can imagine if you had a light bulb that was shining and it's nighttime, and then you give it to your friend and ask them to run away from you, the farther and farther they get, the dimmer the light would appear until eventually you can't see it at all. So we can't just plop a star down somewhere on this diagram. We have to first learn about the distance to that star. And then there's other complicating factors. There might be interstellar dust or other factors that obscure some of the light. Similarly to if I'm looking out of my balcony during the night, if it's a clear night, I can see many, many lights down into downtown Vancouver. But as is often the case here, living in Burnaby or in the greater Vancouver area, it's often not a very clear night and I can't see very far. And so actually utilizing the data that's collected by Gaia requires us to use complex computer models that can essentially predict a star's position on an HR diagram given a set of physical characteristics about the star. So learning those physical characteristics or fitting the computer model is where my role comes in as a statistician, as an astrostatistician. And doing this for potentially millions of stars, as we have here in a globular cluster, is where this becomes an interesting statistical challenge. And so in my work, we've tried to learn about the ages of white dwarfs. So on the left here, I have an image of a white dwarf that's indicated by the arrow. So it's this very small dot here. It's a companion to a much larger star, Sirius. So we tried to learn about the ages of white dwarfs and also the chemical composition of globular clusters. And so what you see here on the right is an HR diagram that we were able to make with data observed from a globular cluster, such as this one that we have here. And the colored curves represent our model fits. So the fact that the curves seem to be going through the observed data means that we were doing a good job. And we were able to learn that this particular cluster hosted stars with different chemical compositions, which informs us about their formation history and how the Milky Way formed and will evolve from the fact that we have different abundances of the element helium. And so I have now a question for you, a trivia question. I have a few of these sprinkled throughout the talk. So some of them I will have kind of said the answer, but in this case I haven't. So this is just trivia. And that is, what is the size or volume of a typical white dwarf star? Is it about the same as Earth, about the same as Jupiter, about the same as our sun, or about the same as twice our sun? So you can vote on that, and then we'll discuss that result. So I'm seeing the results now, and a bit more than half of you said about the same as Earth, and that is correct. So a typical white dwarf star is only about the size of the Earth. And you might think, why that doesn't seem small? The Earth is pretty big. But keep in mind that this is something with the mass of a star, so many, many, many times more massive than the Earth, but it's condensed down into a relatively small volume. So if you were able to get a teaspoon somehow and scoop up a little bit of this of the white dwarf itself, it would weigh several tons. So a teaspoon of it would be equivalent to a few vehicles, for instance. So this is very, very heavy, very, very dense matter. So now I'm going to begin talking about a different application, which was developing machine learning and AI techniques for solar physics. And for this, I'm going to turn it over to my co-presenter, Yue Yan.
Okay, thanks, David. So let's talk about the sun for a bit. People have been studying the sun for centuries. And to learn about the sun, it's not enough to just use our naked eyes. We need some tools. So in this slide, we can see a spacecraft. This spacecraft is the Solar Dynamics Observatory, or SDO. It is developed by NASA, and its goal is to understand the sun and its influence on Earth and near-Earth space. SDO generates about 1.5 terabyte of data per day, and this size is comparable to the full storage of a modern computer. It's great for astronomers to study the sun with such an amount of data. Next slide. So here is the short video that will help you learn more about SDO and what kind of data it collects. Okay.
When you take a picture of the sky, you might see this, an overexposed bright white glare that we know as the sun. In photos, the sun appears white because it emits all the colors we can see at once. Our eyes can only see a narrow range of light, known as the visible spectrum. When they combine together, they make white light. But the sun also emits light that is invisible to the naked eye. These are images from NASA's Solar Dynamics Observatory, or SDO. It was launched in 2010 and has been observing the sun from space in a way that our eyes cannot. SDO uses instruments with special filters to see the sun in 10 different wavelengths of light, including many that we can't see with our own eyes. For us to see them, scientists convert SDO's data to colors we can see. The different colors correspond to different temperatures and regions on the sun. This allows us to study how the sun releases material that can travel across the solar system and affect our technology in space and on Earth. These wavelengths show us the sun's upper atmospheric layers at different temperatures. This wavelength highlights filaments and prominences. These wavelengths highlight the corona, the sun's atmosphere that is much hotter than the sun's surface, and shows features like coronal loops and coronal holes. The wavelengths here reveal the sun's active regions, which have intense magnetic activity that sometimes give rise to eruptions. These wavelengths can see the hottest material in a solar flare. Being able to see constant movement of material on the sun and in its atmosphere can help scientists better understand how our sun behaves and how to track storms that might affect our satellites and astronauts in space or communications on Earth. When you take
Okay, so in the old days, people did not have these sophisticated tools, but they could still study the sun. For example, sunspots, which are dark regions in the surface of the sun, were systematically observed by people in the 17th century. And these people started to notice patterns in the sunspots. Samuel Heinrich Schwab, the person in the left figure, is a German astronomer. He noticed the periodic variation in the average number of sunspots, and he published his finding in 1843. Rudolf Wolf, the person in the right figure, was impressed by this finding, so he also started to observe the sunspots on his own and collect all data on the sunspot activity. Finally, Rudolf reconstructed solar activity back to the 17th century. Next slide. So this plot shows the solar activity in terms of different proxies and how they evolve over time. These proxies measure the level of solar activity, and you can see they include irradiance, solar flux index, sunspot observations, and 10.7 radio flux. They are plotted as lines with different colors. And because they are all proxies of the solar activity, their shapes are very similar. So they all have a roughly 11-year cyclic pattern. There are 3 cycles in this figure. For each cycle, the solar activity level goes from the minimum to the maximum and back to the minimum. That's why you can see 3 peaks in this figure, because there are 3 solar cycles. Okay, next slide. The 11-year cyclic pattern may seem simple, but understanding and predicting these cycles remains one of the big challenges in astrophysics. So here is a statistical model we came up with to predict the solar activity in terms of the monthly average sunspot numbers. In this figure, there are 2 plots. In both plots, there is a gray vertical line, and to the right of that gray vertical line, we have our hindcast or forecast shown as a red or yellow line. In the top plot, we made a hindcast for a past cycle. And because it is a hindcast, we can show the actual observed sunspot numbers as black dots. As you can see, the hindcast, which is the red line, is quite accurate because it is almost in the middle of the observed sunspot numbers. In the bottom plot, we have the forecast for the current ongoing solar cycle. The prediction seems to suggest that the peak magnitude of the current cycle will be similar to the previous one, and the current cycle will reach its peak around July 2025. So information like this can be very helpful for space weather preparation. Okay, back to you, David. You're muted.
Thank you, Yue. So Yue's work was all about trying to learn and predict the solar cycle itself, this 11-year pattern. And this is useful for validating and testing physical models of the solar cycle. But scientists are also interested in developing sort of like a forecasting system for space weather. So similar to the way that we have forecasts for the weather here in Vancouver or wherever you are, which might say it's predicted to rain tomorrow. We want to be able to develop a system that can say, okay, there's a high likelihood of a solar flare or another energetic event. And so that is one thing that I've worked on a little bit. And the way that we sort of approach this is to take advantage of the relationship between sunspots and these energetic events. So sunspots are these dark regions that you can observe on the face of the sun. So don't look at the sun, but if you've done one of these experiments where you project the sun onto a piece of paper, you can actually see these sunspots. So they were first observed around the time of Galileo. And so for this reason, records of sunspots go back quite a bit in time. But now with modern observatories such as SDO, we have very high cadence and high resolution data, and we want to be able to take advantage of this. So transitioning from that video of white light to this video now showing the upper atmosphere of the sun, which shows these loop structures, lets us kind of see the relationship between sunspots and the solar magnetic field. So this region here corresponds to this sunspot here. And these loop structures that you can observe actually trace out the magnetic field of the sun. So when sunspots look rather complex, like this one here, it means that the magnetic field associated with it is also quite complex. And as the magnetic field lines become entangled, as you can kind of see in this video, it increases the chances that the magnetic field lines will break. And when that's happened, a lot of energy is released into space in the form of charged particles. And so predicting these is interesting because when they have these eruptions, as you just saw in the upper video, and then I'll replay again a couple of times, when these eruptions occur, the charged particles, if they're directed at Earth, can have a big impact on our technological infrastructure. So satellites that aren't protected by the Earth's atmosphere can be damaged. But if there's a particularly energetic event, which we know have happened previously in history, with the more recent one being in the 1700s, before we actually had technological significant technological infrastructure, very major events could, it's estimated that they could cause up to about $1 trillion in damage in the electrical grid if it were to kind of impact when North America was, say, facing the sun. So that's why there's a lot of interest in developing even a 24-hour type of forecast, because we could know to be on the lookout and be prepared to, say, shut down portions of the electrical grid if we think that there's a high chance of one of these events. Currently, we don't have as much notice time because we only have from when we observe the event happening to the particles arriving, which is a very narrow window of time. So in this upper right, the white circle represents the sun itself. It's being blocked out so that we can actually observe the coronal mass ejection. And what you see is just a lot of material just being blown off the sun, and that's what releases these charged particles. So these particles are also responsible for the aurora that you might be able to observe if you travel to the northern parts of Canada, or if there's a particularly strong solar flare, it can reach down into the southern parts of Canada and even into the United States. Oops, sorry, I hit the wrong button. Just click back there. And so the reason why this presents a challenge for astrostatistics is simply due to the vast amount of data that SDO is generating. So as Yue mentioned, SDO is generating 1.5 terabytes of data per day, which is about the storage of a modern computer. If you're a little bit older like me, you might think in terms of CDs or floppy disks. So SDO is generating as much, the 1.5 terabytes corresponds to about 5,000 CDs or 1 million floppy disks. So whereas older instruments might have given 1 image per day, SDO, as you saw, is able to generate so many images that they can be stitched together into movies. And so we can't rely on purely manual techniques to analyze sunspots and their complexities and use that to develop an automated system for space weather forecasting. And so this is where I came in as an astrostatistician. So what I did with collaborators was to take images of sunspots in white light, which is what we view in this top panel here. So this is the sun as it were to appear to us if we could actually look at it, which again, don't look at the sun. And we have a companion image, which is called a magnetogram. And so this magnetogram, which is shown here for the sunspot on the top, and this lower panel shows the line of sight magnetic field. So here, regions that appear whiter represent a magnetic field that's pointing outwards from the surface of the sun, and regions that appear darker, so blacker, represent regions of high magnetic field that's directed inwards. So a magnetic field has 2 polarities, positive and negative, and those are represented by the white and black regions in the magnetogram. So regions that are gray means that there's no significant magnetic flux. And the reasons why we look at both sets of images is, again, because magnetic activity is linked to both sunspots, but also to space weather, which we ultimately want to predict. And so because this relationship between sunspots and magnetic activity has been known for a while, scientists have come up with different classification schemes that they can apply to these sunspots just by looking at these images manually and assigning a classification. So one of these, the Mount Wilson classification, named so because it was developed by the Mount Wilson Observatory about 100 years ago, put sunspots into 4 broad classes based on the complexity of magnetic flux distribution. And so complexity is one of these words that it doesn't have a very technical meaning. And so the scientists came up with a set of rules that determines the complexity that then puts these sunspots into 4 broad categories. And I'll describe what these rules are so that you can already understand how to classify such images yourself if you were interested. So the first class of sunspot, as developed by the Mount Wilson observers, is known as the alpha class. And so this is a single unipolar spot, which may be linked with the plage of opposite magnetic polarity. So if you haven't heard these words before, don't worry, I hadn't either when I first started working on this. What you can imagine the alpha class as is sort of like a fountain. So here you can imagine water spurting out from the center and then dispersing around the spot. And so that's, if you were to look at the magnetic field lines, that's how they would appear. So the plage is just these regions that appear a bit brighter or a bit darker in this sort of ring around the central sunspot location, which only has a single pole. And we see just the single spot in the white light image. So this is the simplest type of sunspot, because it just has a single pole and it appears relatively simple in the magnetogram. Next, we have what's called the beta class. So beta is a pair of spots that have opposite magnetic polarity, meaning that it's bipolar, bipolar meaning 2 poles, but with a simple and distinct spatial division between the polarities. So for this, you can imagine if you got just a ruler or anything with a straight line and held it up to your monitor, you can imagine that you could cleanly divide the positive and negative polarity regions represented by the white and the black regions in the magnetogram with just a simple straight line. And then these positive and negative regions correspond to the sunspot clusters that we see in the white light image. Next, we have a beta gamma class, which is a bipolar group. So again, we notice two poles, but it's sufficiently complex that we can't divide both polarities with a simple single straight line. So you can't imagine drawing a line through here that would completely separate the white from the black regions without intersecting one or the other of the polarities. And so as you can see, as we go from alpha to beta gamma, it's getting a little bit more complex each time. And the final class is beta gamma delta, which is a bipolar beta gamma, which includes umbrae of opposite polarity inside a single penumbra. So what do I mean by that? So if you look at the white light images, you can almost think of these sunspots, if you kind of look at them, they kind of look similar to an over-easy egg. So the umbra is the darker region, that would be the yolk of the egg, and the penumbra is the slightly lighter region that surrounds it. So that would be the egg white. So sunspots tend to have this structure where there's a darker region surrounded by a lighter region, and that's the umbra and the penumbra respectively. So now if we look at this spot here, we see that there's 2 umbrae, or at least 2 umbrae. And if we look at this region in the magnetogram, you can see that they have opposite polarity. So that's why this is a beta gamma delta. And the reason why they have this naming structure is because you can imagine the sunspot, if it's not alpha, then it's beta. And if it's beta, beta just meaning that it's bipolar, then it's either has a simple spatial division or it doesn't, in which case it's beta gamma if it doesn't. And then if it also has umbrae of opposite polarity within a side, a single penumbra, then it's beta gamma delta. So we're kind of adding on additional complicated features onto the bipolar sunspots. And each time we give them another portion of the name if they have those features. And so historically, solar physicists would look at these kinds of images and then, as I've said, assign a class manually. This was practical when you only had one or so image a day, but when you have one image per second, this quickly becomes challenging to do even with a team of humans. And another reason why this manual classification isn't exactly ideal is highlighted by the following trivia question. So based on the rules I just described, what type of sunspot do you think that this is? So do you think it's alpha, beta, beta gamma, or beta gamma delta? And I'll give you a hint. We can see that there's two poles, so it's probably not alpha. So it's at least beta. And then whether or not there's a simple and distinct spatial division would make it beta or beta gamma. And whether there's umbrae of opposite polarity with inside a single penumbra would make it beta gamma or beta gamma delta. So I'll give you some time to select your choice, and then we'll discuss those results. Okay, so I'm seeing the results now. Interestingly, no one selected beta. I thought a few people might. Most of you selected beta gamma, and then many of you also selected beta gamma delta. And so the reason why I use this example in particular is because this is a case where there were differing manual classifications. And then when I developed a machine learning based system to do the classifications, it sometimes also disagreed with people. So 58% of you selected beta gamma and 37% selected beta gamma delta. And the choice between the two comes down to whether, if you look at this spot here, you see a slightly darker kind of cluster of a few pixels here, whether that is considered a proper ombre or not, and whether this is considered one sunspot or a cluster of a couple of sunspots is going to determine that difference. And so there isn't necessarily a right answer here. As I've said, when I was developing my approach, we need to rely on manual classifications to train our algorithms, but there were differing answers as to what that classification should be. And so when we're doing science, we obviously we prize reproducibility. We want our results to be reproducible. So the fact that if I gave one set of images to one scientist, they returned a certain set of results, but if I gave it to another scientist and they returned a different set of results, isn't necessarily ideal. So in addition to just the vast amounts of data sort of necessitating automated approaches, another benefit is that we don't have to rely on the inherent human biases that can come with manual classification. And so even if, so our gold standard would be to reproduce the human classifications with an error rate that is on par with what different humans might return if they were asked to assign classes to the same set of images. And so, as I mentioned, I developed, along with collaborators, a machine learning or artificial intelligence-based approach to analyze and classify these sunspot clusters. So we can't just ask the question, is this bipolar? Is there a simple spatial division? We need to have ways of extracting numerical quantities that can be used to enter that question. So this is what's known as feature extraction. But we wanted to guide this with the known science. So with the manual classification scheme that the solar physicists had come up with, within those rules is embedded a lot of scientific knowledge and understanding. And so we would extract features such as the smoothness of the line that separates the two polarities. So beta gamma should have a rougher line than betas. And then after extracting sets of numerical features, we used a machine learning technique known as random forest, which is just an ensemble of decision trees. So decision trees are a class of machine learning algorithms that are actually quite simple to understand. Their names come from decision trees that you might have encountered in a completely different context, where we can separate our data into different classes by asking a series of kind of yes, no type questions. So again, if it's unipolar, then it's an alpha sunspot. If the answer is no, then we ask, is there a simple dividing line? If yes, then it's a beta. If no, then we ask if there's a delta spot. And then that final layer in the tree determines whether it's beta gamma delta or just beta gamma. So the algorithm works by taking random sets of these numerical features and building decision trees off of those numerical features. And the end result is an automated classification algorithm that allows us to process large batches of these images and go a bit beyond what we can do with manual classification and start to look at the evolution of the sunspot, which we believe will better enable us to predict space weather. So now I'll come to the last application that I'll talk about, because I do want to leave time for questions as well. And this is looking at machine learning for cosmology. So this graphic here presents a brief history of the universe, with apologies to Stephen Hawking for stealing that title. So our current understanding of the universe is that it began roughly 13.77 billion years ago with the Big Bang, and then immediately inflated. And there's this afterglow pattern that occurred 375,000 years after the birth of the universe that we can actually observe. This is known as the cosmic microwave background. And then for about 400 million years, there really wasn't anything of interest happening in the universe. It was the so-called dark ages. The first stars were formed about 400 million years after the Big Bang. And then over the next billions of years, more complicated structures formed and developed, such as galaxies, planets, so solar systems, and the kinds of large-scale structures that we can observe today. And so we've known for a while that the universe has been expanding. So the large scale structures in the universe are moving farther away from one another. But a recent discovery is that this expansion is actually itself accelerating. So we thought that it would maybe be slowing down, that eventually the expansion would stop and everything would start moving back towards, the expansion would turn into a contraction. But instead, it seems like things are expanding faster. And this discovery led to a recent Nobel Prize in physics, and I think around 2007 or so. So this was really surprising because it didn't really agree with our understanding of the universe and our models for cosmology, which represent our understanding of the universe. And so to better understand cosmology and the history and to be able to predict the future of the universe, one type of object that's been studied are known as type 1a supernova explosions. And so these are energetic events that we believe one story for how they form is when we have a white dwarf star. So remember I talked about white dwarfs earlier, and I said that they were just the remaining core of a star after it's no longer undergoing nuclear fusion. But if that white dwarf happens to be close enough to a larger star, and this can happen because many stars form in pairs, then that white dwarf can accrete matter from the larger star. So the white dwarf can become more massive because it's stripping matter off of its companion star, as you can see here. Whoops. And then once that white dwarf star reaches a certain mass, once it passes what's known as the Chandrasekhar limit, then the type 1a supernova explosion occurs. And these are extremely bright, extremely energetic events. And the reason why these are of interest to scientists who are studying the universe is because of that, of how the type 1a supernovas occur. Because the explosion happens when the white dwarf reaches a certain mass limit, it's thought that they all have the same brightness. So the same absolute brightness, meaning that if they were all the same fixed distance from the Earth, then we would notice that they have the same brightness. And they're called type 1As as opposed to other types of supernovae or not supernovae because they all have a characteristic light curve. So that is what is given here on the right. So the light curve is the brightness over time, so as a function of time. And so the reason why these objects are so useful for studying cosmology is because if we know that they all have the same absolute brightness, and we notice one of these explosions happening in a galaxy that's far away, we can compare how bright the supernovae appears to how bright it would appear at a fixed distance, and we can use that relationship to then learn the distance to the galaxy in which that supernovae lies. And so they form what's been called a cosmic distance ladder. And so if we can better learn the distances to various objects in the universe, we can learn about how the universe is expanding, and we can refine our models of cosmology and predict certain physical quantities, such as the amount of dark matter and dark energy in our universe, and predict kind of how our universe will continue to evolve billions of years into the future. And so where does statistics come into this? So if I were to give a figure like this to astronomers, to cosmologists, they would be able to tell you the different types of supernovae based on how these light curves appear. And in particular, as I said, the type 1As have a very distinct pattern where there's a very quick rise and then this kind of steady fall that's quite sharp, as opposed to type 1Bs or the other type of supernovae that we have here. And so in the past, this has actually been done. So astronomers and cosmologists looked at light curves to try to find supernovas. But as has been the theme of this talk, modern observatories make this kind of manual classification impossible. So in particular, there's an observatory called the Rubin Observatory that's expected to begin observations in the later part of next year. And it's going to conduct a deep survey over a large area of the night sky every night, collecting data on billions of objects. And so before we said that SDO collected a lot of data because it had 1.5 terabytes of data per day, the Rubin Observatory is expected to produce 20 terabytes per night, which corresponds to 70,000 CDs or more than 10 million floppy disks per night, and about 500 petabytes over the course of its operations. So that's nearly 2 trillion CDs, and I didn't try to calculate the number of floppy disks. I don't actually know the name of the numbers that are that big. And so when you're looking now at trying to look at billions of objects every single night, it's just simply impossible to be able to do this kind of classification manually. And even if it somehow we trained lots of people to look at these images every single day, we would still lose the ability to notice when something is happening in real time. And so that's a challenge for people who are doing astrostatistics, is to not only be able to automatically classify type 1A supernovas using machine learning and AI techniques, but to be able to say when one is occurring so that we can point other observatories at that portion of the sky and collect data that will be really useful for learning about physics. So now I come to the final trivia question, which is related to the composition of the universe. So we collect this data because we want to learn about the universe. And part of this data helps us learn about the composition. So approximately how much of the universe is comprised of normal matter as opposed to dark matter and dark energy? And this isn't something I mentioned in the talk, so this is just as trivia, and then we'll talk about the result once you've finished voting. So most of you said 5%, which is the correct answer. And that kind of, I think, is something that is baffling to me a little bit. So the matter that makes up us and everything that we can see around us, everything we can interact with, according to our current understanding of cosmology and physics, makes up only 5% of the stuff that's out there. The remaining, of the remaining 95%, about 25% is thought to be dark matter, and the rest is thought to be dark energy. And so I'm going to skip the last application in the interest of time, and because I've talked about it in previous Meet an SFU Scientist events. And I'll conclude by saying that if you're interested, if you have an interest in science and want to do something that actually contributes to astronomy and astrostatistics in particular, I would encourage you to check out the citizen science projects at what's called the Zooniverse. So as you've heard me say, a lot of the data that I rely on to develop machine learning or other statistics-based techniques for analyzing modern data comes from the kind of painstaking, manually classified or manually analyzed data from both other scientists as well as from the public through projects such as this. So we need data to train our algorithms, and citizen scientists, including myself, have been quite helpful in that regard. So I'll conclude by just saying thank you for attending this event, and I'll answer any questions that you may have.
Thank you so much, David, and thank you, Yue, for this presentation. And I appreciate all those who answered those trivia questions. It was fun seeing the results from each of those trivia questions. And we have a few questions coming in, and I will read questions as we receive them. The first question is related to that last trivia question you had posted on the page, is how do we know that only 5% of the universe is normal matter?
So it's based on the physics models. So depending on the amount of normal matter, it affects the way that galaxies, the motion of galaxies and the motion of stars within galaxies. It basically doesn't behave as if our current understanding of gravity is correct, then it does. Then objects that we can observe don't obey kind of the current understanding of physics. So it means that there's more stuff out there than is explained by simply all the matter that comes from what we can actually observe. And then there's physics models that, depending on what we can observe, tell us how much of the excess matter is expected to be dark matter or dark energy. So I said the universe is expanding, and that expansion is accelerating. So the rate of that is determined by things like the amount of dark energy. And so that's why it's helpful to learn the distances to objects very precisely, because it helps us reduce our uncertainty on these other physical parameters.
Right. There's another question here. I've heard it said that a white dwarf is a diamond. Is this true?
So that's a very good question. So one of the scientific goals I had when I was working on that project was to learn the composition of some of the white dwarf stars that are in our galaxy, because that informs other physical theories. And because of nuclear physics, how it tends to work, the stars burn through hydrogen and helium. Most white dwarfs are composed of carbon and oxygen. And some white dwarfs are thought to be composed of only carbon. And if you think of what a diamond is, it's just a hunk of carbon that's been greatly compressed. And we said that white dwarfs are extremely dense. And so it is thought that some white dwarfs might have a core that's just basically a giant diamond. So if you could somehow go out and get there, it'd be worth more money than I think there's even a number for. But extracting it would probably be impossible. But it's something maybe nice to think about, that some of the stars that we can observe are these twinkling, literally jewels out in space.
Right, right. Next question is, what can you do with gamma ray, and what does gamma ray do?
So I'll go back to the first slide where I mentioned gamma rays. So the different parts of the electromagnetic spectrum reveal different features of the universe. So collecting gamma rays, X-rays and gamma rays, is difficult because they're very energetic. But if we're looking for certain types of bursts and other kind of very energetic phenomenon, it only appears in gamma rays. So what we can actually see in the visible portion of the spectrum is a very small part of what's actually out there. And if we look in other parts of the spectrum, gamma rays, but also on the other side, radio waves, we can, quote unquote, just see more of what's out there.
Right. This next question is probably for you, Wade, about solar eruptions. What are solar eruptions actually consisting of? And how can we detect solar eruptions and solar flares?
I think David will be more suited for the question.
Sure. So eruptions, so a solar flare is pretty much just a burst of charged particles. Coronal mass ejections are named such because there's actually matter of the sun that's ejected into space when this occurs. So if you kind of saw that in that video, that it appears like there's like a little arm that comes out of the sun and just flings off some of its stuff into space. So it is actually like part of the solar plasma. So the sun isn't a gas, it's a plasma, which just means that it has an electrical charge. That's why it has magnetic fields. And some of this plasma can actually be ejected into space. And when that happens, charged particles are also ejected along with it. And then this is what can cause havoc for our electrical infrastructure. And with instruments such as SDO, we can actually see this happening. So that was shown in some of the movies that I played, where you can actually see a flare or a coronal mass ejection, looking in the different wavelengths of light that we measure the sun in.
Mm-hmm. Thank you. Next question is, could solar flares be harnessed as an energy source for space travel?
So yes and no. I don't know if I would say solar flares per se, because they're kind of unpredictable. It would kind of be like, the analogy I'm going to use is that we have geothermal energy, but we don't try to harness, like, say, volcanoes. But what we can do is, because the sun is always radiating energy into space, they do have what are called solar sails, which kind of use the energy that's output from the sun to harness like a literal sail that can be used to send out probes and other types of instruments into space, and maybe one day even craft that could hold people. So it's literally like sailing on sunbeams. And if you're interested in that, there's some citizen science projects that have been launched recently and funded by citizen scientists to test these technologies.
Mm-hmm. This next one is interesting. Is the MOND alternative to dark matter hypothesis gaining any traction lately?
So MOD stands for Modified Newtonian Dynamics. This isn't my area of expertise. I knew someone when I was do my undergrad, who was a grad student working on this. So as I mentioned that the current accepted understanding of cosmology is that there's kind of missing mass that has to be present to account for the behavior that we observe in galaxies and other astrophysical objects. And I mentioned, like, if our understanding of physics is correct. So one alternative to this is maybe our understanding of physics isn't correct. So we assume that kind of physics works the same throughout the universe, but maybe it doesn't. And so some scientists have tried to modify physics, modify Newtonian dynamics to try to explain the observations without introducing dark matter and dark energy. My understanding as a layman is that there's still evidence of dark matter that isn't just from the dynamics. Something called the bullet cluster, I believe, has been shown to actually have dark matter clustered in it. But I wouldn't be the right person to wage into that scientific debate between different cosmologists, I'll say. I'm going to be diplomatic and diplomatic about that.
Fair enough. So I'll pick up the last two questions. And the next one is, why does the solar cycle follow an 11-year cyclic pattern?
So that's an excellent question. And the result, the answer is that this is something that's not really well understood. So despite the fact that the solar cycle was first observed back in the 16 and 1700s, and we've been collecting data on sunspots and other features that follow that cyclic pattern, an actual physics understanding of the solar dynamo, the mechanism that generates that 11-year pattern, is a big unanswered question in solar physics. And so part of the contribution of Yue's work that he described is to see whether we can use a purely statistical approach, purely empirical approach that only uses the observed data to predict features of the upcoming solar cycle, and then compare these against purely physics-based models that also try to reproduce features of the solar cycle. And then there's this kind of trade-off back and forth where we can hopefully better refine the physics model and ultimately lead to that better understanding of why there's this cyclic pattern and why it maybe follows a roughly 11-year cycle. But this wasn't something that resulted from physics. This was something that was purely observational.
Thank you for that. I'll end with this last question on the Q&A box. Can you discuss the commercial aspects of acquiring your data?
Sure. So obviously these are expensive instruments, and all upcoming observatories cost in the billions of dollars. So that's why they tended to be funded by large international collaboration, so that no one group is bearing the full burden of that cost. So there is certainly a financial cost to it, and there's other considerations as well in terms of where we build these observatories. So I didn't talk about something called the 30-meter telescope, but this is one that's being proposed to be put on top of Mauna Kea. I'm probably pronouncing that wrong, but on top of Mauna Kea in Hawaii. And so there's concerns there about the indigenous communities that have inhabited that area, and whether it's being respectful to them, and then whether the environmental degradation of clearing land for it, and so on and so forth. So this is something that astronomers and scientists in general should be and are trying to be mindful of the cost, both economic and opportunity and environmental and otherwise, in what we are trying to do.
All right. Well, thank you so much, David, and thank you, Yue, for staying with us today and doing this presentation for Meet an SFU Scientist. And I especially want to thank all those who've joined us in this session today. We appreciate all the questions you've typed into the Q&A box and for answering the trivia questions posted by our presenters. And thank you so much for engaging with us this afternoon. We will be sending a feedback web survey to all those who've attended today. And this is, again, all part of Science Rendezvous. And we hope to see you again for next year when we stage Science Rendezvous event, sometime May next year, 2023. If you have any feedback or any suggestions that you have or comments you just want to share, please email sfuscienceoutreach@sfu.ca. My name is Cynthia, and we appreciate your joining us today. Have a great rest of your evening. Thank you all for joining us.